In this video, we're going to be talking about applications to physics and engineering. First, we'll start off by talking about hydrostatic pressure and force. In this section, we are going to submerge a vertical plate in a liquid, usually water, and we want to know the force that is exerted on the plate due to the pressure of the liquid. This force is often called the hydrostatic force. If we are d meters below the surface of the fluid, then the hydrostatic pressure is given by P equals rho times g times d. This is the Greek variable rho, where rho is the density of the fluid and g is the gravitational acceleration. If the liquid is water and we are using the metric system, then the density is equal to 1,000 kilograms per meter cubed, and the gravitational constant is equal to 9.8 meters per second squared. Assume that a constant pressure, capital P, is acting on a surface with area, capital A. Then the hydrostatic force that acts on that area is force equals pressure times area. Note that we won't be able to use this formula to find the hydrostatic force on a vertical plate since the pressure will vary with depth and hence will not be constant as required by this formula. Here is a table with various measurements in the metric system and the US customary system. Sometimes you'll also hear this called the imperial system. And go ahead and pause the video if you'd like to read over the table and look at the various measurements. Some notes at the bottom is that the weight density given by delta, this is a lowercase delta, capital delta looks like a triangle, is equal to rho times g, where rho is the density and g is the gravitational constant due to acceleration. And the weight density of water is 62.5 pounds per cubic foot. And then the second note is that in 2 dimensions, mass is equal to the density times the area. If we're in 3 dimensions, then we have that the mass is equal to the density times the volume. Example 1 says a vertical plate is submerged in water and has the indicated shape. Express the hydrostatic force as an integral and evaluate it. Now, the very first time I taught Calculus 2, I had a student come up with this wonderful mnemonic device to help you remember how to set up your integral. And that mnemonic device is ducks, glide, down, lakes. Okay, so our force is equal to the integral from C to D of our first D for ducks stands for density, then gravity, then depth, and then the L in lakes stands for length. And we'll be integrating with respect to y. So I usually make this recommendation to my students. I think that it's much easier when you're setting up your coordinate system by having your bottom of the plate align with the x-axis. And then we'll have the y-axis go straight down the middle like that. There's our y-axis. And if I were to draw a cross-section here, here's my cross-section. This dimension here is delta y. And the length of this, in this case, this here is 2 feet. Which is captured right above that. So let's go ahead and start to set up our integral. We have the force is equal to, now the limits of integration are, where are my cross sections starting? So my very bottom most cross section starts at y equals 0, and then it ends here at y equals 8. So I'm going to have my integral from 0 to 8. Now, we are in the US customary system right now because our measurements are in feet. So our density times gravity here is going to be the weight density of water. So 62.5 combines those two numbers. So we have 62.5. Then the depth is going to be, if we come back to our picture, if I have my cross section, the one in the middle there, and this distance here is y, And then the depth is the distance basically from like how far my cross section is from the surface of the water. So I know that from the bottom of my tank to the surface of the water, if I add 8 and 3, that gives me 11 feet. And so the distance that my cross section is from the surface of the water is captured by this dimension here, and that is going to be 11 minus y. So here my depth is 11 minus y. And then this problem's really nice because my length of each of the cross sections is constant. So I'm just going to put a 2 here, and we are integrating with respect to y. I'm going to go ahead and multiply my two constants together. 62.5 times 2 is 125. And then in my integrand, we are left over with 11 minus y dy. Let's go ahead and integrate now. So I have 125 times 11y minus y squared over 2. And we're evaluating this from y equals 0 to y equals 8. And 11 times 8 is 88. And then we have 64 divided by 2, which is 32. Now, if we multiply those numbers together, this is going to end up equaling 7,000. And we are measuring a force here in the US customary system. So the units on this is going to be pounds. Our final answer is that the hydrostatic force is 7,000 pounds. Example 2 says a vertical plate is submerged in water and has the indicated shape. Express the hydrostatic force as an integral and evaluate it. So just like in the previous example, I want to set up my coordinate system so that my x-axis aligns with the bottom of my plate, and then I'll have the y-axis go straight down the middle like that. Now here at the bottom of my plate, we have the ordered pair 0, 0, and then here I need to figure out that ordered pair. If I know that this is half of 2, so my x-coordinate should be 1, and I'm going to need to figure out the height of my triangle. Now, let's quickly sketch out this triangle. And this is an equilateral triangle, so all of the side lengths are 2 meters. And if I were to cut this in half, this would form a right triangle. And because it's an equilateral triangle, every interior angle must be 60 degrees. So here this is 60 degrees. And then here, because I'm cutting this in half, that is going to be 30 degrees. Now, I know from earlier that that is 1, and this turns out to be a special right triangle. So let me erase part of this. So here I have a 30, 60, 90 triangle, and if I were on the unit circle and I were scaling this down, this would still be 30 degrees, this would be 60 degrees, and if we're on the unit circle, the hypotenuse would be 1, and then for a 30, 60, 90 triangle on the unit circle, this would be 1/2, and then this would be √3 over 2. So moving from this direction, we can see that each of the side lengths are being doubled. So this dimension of my larger right triangle would be the square root of 3. So going back to this ordered pair, that would be 1, square root of 3. Why am I looking for those ordered pairs? Well, eventually what I'm going to need to do is if I drew a cross section here, I know that this dimension is delta y, and if I called this point here just x, y, then I would need to find the length of this cross section. And looking from the picture, I can see that this dimension here is x, but I'm going to end up needing to multiply it by 2 to get the entire length of my cross section. So let's really quickly write down my mnemonic device again. We have ducks, glide, down, lakes, and this is going to help us to form our integral. So the hydrostatic force is equal to the integral from, if I start my bottommost cross-section, that's going to start at y equals 0, and it's going to end at the square root of 3. Then we have our density. We're in the metric system in this example, and we're dealing with water. And so the density of water is 1,000 kilograms per meter cubed. Then G stands for gravity, which is 9.8. Then the depth. So coming back to my picture, I know that this distance is y. I know that the distance from the surface of the water to the bottom of my tank is the square root of 3. And so my depth is going to be the square root of 3 minus y. And now we need to solve for the length. In our previous example, the length of each cross-section was constant, but because of the shape of this plate being a triangle, the length of each cross-section changes and is no longer constant. So that is why we found these ordered pairs. I want to think about the slope of that line segment so that I can create an equation for this line segment. And the line segment I'm referring to is this line segment here. And that line segment goes to the point 0, 0, and 1 comma square root of 3. So if I use rise over run, the rise is square root of 3, and then the run is 1. So my slope in this instance is the square root of 3. Also, my line segment is going through the origin. So if I were to create a linear equation for this line segment in the form y equals mx plus b, our b value is going to be 0 since it's going through the origin. So the equation of that line segment is y equals the square root of 3 times x. Now, we're going to be integrating with respect to y, so I need to solve this equation that we have here for x, and I'm going to do that by dividing both sides by the square root of 3. And remember, here we said earlier that not only do we need to solve for x, but we need to solve for 2 times x, or x plus x. So this implies here that 2x is equal to 2y over the square root of 3. So I'm going to go ahead and put that here, 2y over the square root of 3, and that expression represents the length of our cross-section. So let's continue. The force is equal to, I'm going to go ahead and multiply my constants together. So I have 1,000 times 9.8 times 2. And I'm going to pull that outside of my integral. That ends up being 19,600. And then I'm also going to factor out the square root of 3 that's in my denominator right now. And then we have the integral from 0 to the square root of 3 times the square root of 3 minus y dy. Now we can just use the power rule to integrate this thing. So it's going to give us force is equal to 19,600 over the square root of 3 times the square root of 3y minus y squared over 2. And this is being evaluated from y equals 0 to y equals the square root of 3. Looking back, I'm realizing that I did not distribute this y in, so I'm going to go back and fix that. So I have the square root of 3 times y minus y squared dy. And when we're integrating now, this is going to be root 3 over 2 y squared minus y cubed over 3. Okay, that's looking better. So let's go ahead and plug in our limits of integration. So this is going to give us 19,600 over the square root of 3 times 3 root 3 over 2 minus 3 root 3 over 3. And what's going to happen now is if I distribute in the 1 over the square root of 3, these will cancel out. And so that's going to give us force is equal to 19,600 times 3 halves minus 1, which is 1 half. And if I cut that in half, that is going to be 9,800. And because we're in the metric system, this is being measured in newtons. So there we go. That completes this example. All right, so in example 3, we have another vertical plate, and we're asked to find the hydrostatic force. Now, this is the first example that we're taking a look at where only part of the plate is submerged, and so that's going to affect things a little bit differently. I still want to make sure that my x-axis aligns with the bottom of the plate, and then I'm going to have my y-axis go through the center like normal. And now what I want to do is I want to identify these ordered pairs in quadrant 1. So the lower ordered pair is 4, 0. I know that we're cutting 8 in half to get 4, and because it lies on the y-axis, or excuse me, the x-axis, the y-coordinate is going to be 0. This ordered pair here is 2, 3. I can see here that this height, if I add those, 1 plus 2 is 3, so that's my y value. And then for the x value, I'm cutting 4 in half to get 2. And just like in the previous example, I'm going to need to find the equation of this line segment here so that when I have a cross-section, I am able to find the length of that cross-section. And the thickness of this is delta y. And I know that this point here is an ordered pair x, y. So from here to here, this is y. And I can see that from the surface of the water to the bottom of the plate, that distance is 2. So the depth of my cross-section is 2 minus y. Okay, so my mnemonic device is ducks glide down lakes. So when we're coming up with our limits of integration, we're thinking about where do my cross-sections start and where do my cross-sections end. But because we're talking about hydrostatic force, that is the force that is being applied to the plate by the water. So the uppermost cross-section is going to stop at y equals 2 because after that, the plate is no longer submerged in the water, so there's no force being acted upon the plate by the water after 2. So my lower limit of integration is 0, and my upper limit of integration is 2. Now, we're in the US customary system, so I'm going to have this be the weight density of water, which is 62.5. Then I'm going to multiply by the depth, which is 2 minus y. And then now we're going to need to solve for the length, and let's remind ourselves that we are integrating with respect to y. So I want to find the equation of the line segment. It's of the form y equals mx plus b. And I'm going to solve for the slope by using the slope formula, y2 minus y1 over x2 minus x1. And so that's going to be equal to 3 minus 0 over 2 minus 4. Hopefully you can recognize from the picture that the slope of that line segment's negative, so if you get a positive number, you probably did something wrong, like I was just about to do. So 3 minus 0 is 3, and then 2 minus 4 is negative 2. So our slope ends up being negative 3 halves. Now, in this case, our line segment's not going through the origin, so we actually have to solve for our b value. We have y equals negative 3 halves x plus b, and I'm just going to plug in the ordered pair 4, 0 for x and y. And then this implies that 0 is equal to 3 times 4 is 12. 12 divided by 2 is 6. So we get negative 6 plus b. And then if I solve for b, I get b equals 6. I'm trying my best to differentiate my b and my 6 because typically they look pretty similar. So b is equal to 6. That means that the equation of my line segment is negative 3/2 x plus 6. So how is that helping us find the length? Well, I need to solve this equation for x. So I'm going to subtract 6 on both sides to get negative 3/2 x is equal to y minus 6. And then I'm going to isolate x. So we get x is equal to negative 2/3 times y minus 6. And I'm going to go ahead and distribute in the negative 2/3. So that's going to be negative 2/3 y. And then, let's see, 2 times 6 is 12. Divided by 3 is 4, and it's going to be positive. All right, so we have the equation x equals negative 2/3 y plus 4. And my x value tells me the distance from here to here. That's x, but the total length of my cross-section is x plus x, or 2x. So from here, I want to multiply both sides of my equation by 2. And so that will give me 2x is equal to negative 4/3 y plus 8. So now that expression represents my length of my cross-section. Okay, so now at this point we have force is equal to, I'm going to factor out 62.5. And we have 2 minus y times negative 4/3 y plus 8 dy. All right, so I went ahead and I multiplied this out, my integrand, using my favorite method, the box method, to multiply out polynomials, or So let's go ahead and start integrating now. We have the force is equal to 62.5. And then I'm going to use the power rule. So I have 4 over 3 times 3 is 9, y cubed minus 32 divided by 2 is 16. So it's going to be 16/3 y squared plus 16y. And I am evaluating this between y equals 0 and y equals 2. Now I want to plug in 2. Notice that if I plug in 0, everything's going to become 0, so I just need to ultimately plug in 2. So my force is equal to 62.5 times 4 over 9. 2 cubed is 8. Let's see, 16 over 3. Times 4 plus 16 times 2. I'm just going to throw that into a calculator, and if I round that, that is 888.89 pounds, because we are in the US system. All right, that concludes this example and this video on hydrostatic pressure and hydrostatic force. Tune in to our next video where we're going to be talking about centers of mass, which is really exciting stuff, and it has a lot of really cool applications in physics and engineering.